In our previous lecture, we started our discussion on input-output configuration of instruments. We were trying to develop a generalized configuration that represents significant input-output relationship that exists in an instrument. In this context, we defined three different types of inputs. We said that input quantities can be broadly classified into these categories. Desired inputs, we define desired inputs as the quantities that the instrument is designed to be measured. So, the instrument has been designed to be sensitive to desired inputs only. Interfering inputs, quantities that unintentionally affect the instrument as a consequence of the principles used to acquire and process the desired inputs. And modifying inputs are undesired quantities that affect the output by altering the input-output relations for desired and interfering inputs. So, we presented this block diagram in previous class, which represents a general input-output configuration of instruments. You have desired inputs, modifying inputs and interfering inputs. Let us consider this as a transfer function which works on desired input. This one, or let us first consider this, the transfer function which works on interfering input. And since modifying input alters the relationship that exists between desired input and output and interfering input and the output, we have a transfer function TFMD which alters, which represents interactions between these two, and a transfer function which alters the which interacts with modifying input and interfering input. So, you can consider that this transfer function which works on the desired input signal gives us an signal which can be considered as component of the final output, and this component is due to desired input as well as modifying input. Similarly, the component here is the result of interfering input as well as modifying input. When these two components are summed up, we get the final output. It can also be represented by a more simple block diagram like this, where the instrument receives not only the signal corresponding to the physical variable we are interested in measuring, but also interfering input as well as modifying input. So, the instrument receives all these different types of inputs and finally responds with its output. So, let us now take some example of desired inputs, interfering inputs and modifying inputs. First, let us consider a manometer. We are considering a U-tube manometer. You know, U-tube manometer is used to measure differential pressure. Let us consider the two limbs of the U-tube manometer is connected to two different pressure sources. We consider P1 to be greater than P2. and there is manometer liquid. So, if P1 is greater than P2, this difference of liquid level between these two tubes, if we call it x, x can be considered as a measure of P1 minus P2, the differential pressure. So, desired input here is P1, P2 or the differential pressure. Now, let us take the same U2 manometer and put it in a vehicle which is accelerating. So, we have the same U2 manometer we put the U2 manometer on a vehicle that is accelerating. Now, even if we apply same pressure to both the limbs of the manometer, we will see a reading. We are considering here, let us P1 equal to P2. If P1 is equal to P2 and if this is not mounted on a vehicle which is accelerating, x should be equal to 0. But if I mount the U2 manometer on a vehicle which is accelerating, and even if the limbs both the limbs of the U2 manometer is connected to same pressure source, it will show a differential pressure reading. So, acceleration is working as an interfering input. The manometer has become unintentionally sensitive to acceleration. Similarly, if you tilt the manometer with an angle, then also you can see that even if both the limbs of the manometer are connected to the same pressure source, the manometer will show a non-zero reading. So, the tilt angle again works as an interfering input. So, what can be the modifying input here? We know the modifying input changes the relationship that exists between input and output, or in other words, it affects the transfer function between the desired input and the output, and also interfering input and the output. We know temperature affects the density of the manometer liquid. So, if temperature changes, the change in temperature will affect the manometer reading. Since the density of the manometer liquid will play a role in the calibration of the manometer, and the density changes with time, density changes with temperature, so the temperature can act as modifying input. Let us take still another example. Let us take an example of strain gauge. A strain gauge is a device which measures the strain of a specimen. This is an example of a strain gauge. We will talk about strain gauge in more detail later. For the time being, let us consider this is a simple resistance wire. Now, this resistance wire is cemented on a specimen. So, if the specimen is strained, the resistance wire also gets strained. Now, the resistance wire when strained, it will change the resistance of the resistance wire. So, if I take help of an Wheatstone bridge and put the strain gauge here, and then first maintain null point, and then I strain the specimen, so the resistance wire gets strained, which will cause a change in the resistance of the strain gauge. So, there will be an unbalance in the circuit, and the current can be taken as a measure of the strain. So, the desired input here is strain. The strain gauge has been designed to be sensitive to strain. But the temperature can act as an interfering input, because temperature can change the gauge resistance even if there is no strain on the gauge. Because the resistance of the wire is a function of temperature, and if there is a change in temperature in the ambient, the gauge resistance can change, which can show an unbalanced current in the circuit. So, temperature works as an interfering input. Temperature can also change the gauge resistance due to the strain resulting from the differential expansion of the gauge and the specimen. Ordinarily, the strain gauge and the specimen will be made of materials with different thermal expansion coefficient. So, a change in temperature can cause differential expansion of the gauge and the specimen. So, this can cause a strain, and again temperature this way also works as interfering input. Temperature also works as a modifying input here, because gauge factor is dependent on temperature. We can define the gauge factor of this strain gauge as change in resistance, change in gauge resistance is equal to gauge factor multiplied by gauge resistance when unstrained multiplied by unit strain. Since gauge factor depends on temperature, so temperature will work as modifying input. So, next let us talk about what we can do to make our instrument respond to only desired input. So, we want to filter out the effect of or the spurious effect of modifying input as well as interfering input. Now, method of signal filtering uses filters to block the undesired inputs. So, we can block the undesired inputs, namely modifying input as well as interfering input, by introducing suitable filters. The filters may be applied to input signal as well as output signal. Depending on whether we apply the filter to input signal or output signal, we can have input filtering or output filtering. So, this is a corrective measure for undesired inputs. In case of input filtering, we want to apply the filter to input signal so that it blocks the undesired input. Again, let us consider the block diagram which represents the relationships between desired input, modifying input, interfering input on one hand and the output on the other hand. I want this output to be sensitive to desired input only, but the instrument also responds in the process of being sensitive to desired input only to modifying input as well as interfering input. So, if I can introduce a filter here and if I can design a suitable filter, it may block the modifying input. In other words, you can consider that I want a transfer function here which is actually 0. So, when I aim the input modifying input is being worked upon by a transfer function which is equal to 0, will give a signal equal to 0. Similarly, to block the effect of interfering input, I can introduce a suitable filter here. Again, mathematically speaking, or in terms of our block diagram notation, we should have a transfer function here which is equal to 0. If we can do that, this component will be, this signal will be essentially 0 and this signal will be void of effect of modifying input. So, this final output will be solely result of desired input. So, by introducing suitable filters to input signal, it is possible theoretically to make my instrument sensitive to desired input only, or to make my measurement to be sensitive to desired input only. I can also introduce filters to the output signal. Again, consider the same block diagram. In case of input filtering, we put filters to the modifying input signal as well as to interfering input signal. In case of output filtering, we will introduce filters at output signal. So, if I can split this output here, which is a result of desired input, modifying input as well as interfering input, if I can split this output signal into components of output component coming from only desired input, output component coming from only modifying input an output component coming from only interfering input, and then introduce filters to the component that comes from modifying input to the component that comes from interfering input, my final output will be sensitive only to desired input. So, the concepts are very much similar. In case of input filtering, we will introduce filters to input signal. In case of output filtering, we introduce filters to the output. So, now let us take an example of input filtering. Let us consider a thermocouple. Thermocouple is a temperature measuring instrument. It is made of two dissimilar metals. We will talk about thermocouple in more detail later. Thermocouple is made of two dissimilar metals. We make two junctions. One we call measuring junction, another one is called reference junction. So, if you take two dissimilar metals, let us say metal A and metal B, and form two junctions, if you keep these two junctions at two different temperature, then EMF is produced. And this EMF depends on the difference between these two junction temperature. So, now if I keep one junction temperature constant and call this as reference junction, and expose this junction, which I call measuring junction, to the measuring medium whose temperature I want to measure, then this EMF produced can be taken as a direct measure of the temperature. The EMF produced depends on the difference between this junction temperature and this junction temperature, but by keeping one junction temperature constant, I can measure the temperature directly by looking at the EMF value, of course, after suitable calibration. So, now let us come back to this. This is same as this. So, you have an EMF measuring instrument here, a millivoltmeter. The EMF is of the order of millivolt. Now, this reference junction has to be kept at some constant temperature. So, if there is varying ambient temperature, this can work as an interfering input to the thermocouple. So, one way to put a filter to block the effect of varying ambient temperature will be put a thermal insulation around the reference junction. So, by putting a thermal insulation around reference junction, I can block the effect of varying ambient temperature. So, this is an example of input filtering. Again, another example of blocking the effect of interfering input can be seen in strain gauge. We just talked about strain gauge, which measures strain in a specimen. Consider this to be the strain gauge put in one arm of the Wheatstone bridge. We know the unbalanced current is a measure of the strain in the specimen. Now, the strain gauge can become sensitive unintentionally to magnetic field. So, to block the effect of interfering magnetic field, we can put a magnetic shield around the circuit. So, you have a magnetic shield which blocks the effect of interfering magnetic field. So, again this is an example of input filtering. Another way of taking corrective measure for undesired inputs will be method of opposing inputs. Here we intentionally introduce an input that cancels the effect of undesired inputs. So, we will introduce intentionally an input to the instrument that tend to cancel the bad effect of modifying input and or interfering input. Let us look at this block diagram. We have desired input corresponding transfer function. We have interfering input corresponding transfer function. We intentionally introduce this interfering input. We have this unavoidable interfering input. So, we have a desired input signal, we have an interfering input signal which is undesirable, which is unavoidable, but we intentionally introduce another interfering input signal, and we choose this signal such that the effect of unavoidable interfering input signal and the intentionally introduced interfering input signal cancels each other out. So, this is essentially a zero signal. So, the final output becomes this component alone, or in other words, the final output becomes result of desired input alone. So, let us now take an example of method of opposing input. We know millivoltmeter is essentially a current sensitive device. But the scale of a millivoltmeter can also be calibrated in volts, because volt and current are related. Let's consider a schematic of millivoltmeter. So, you have the coil. Ambient temperature works as modifying input here. Because the ambient temperature can cause a change in the coil resistance. So, how do I nullify the effect of ambient temperature? We can add another resistance into the circuit and its material is such that it has a temperature coefficient of resistance opposite to that of coil. Ambient temperature can change the resistance of the coil. So, it can work as a modifying input. Now, if I add a compensatory resistance in the circuit and I choose the material such that it has a temperature coefficient of resistance opposite to that of coil, I can cancel out the effect of ambient temperature. So, this is an example of method of opposing input. I intentionally introduce a resistance to cancel out the effect of ambient temperature on the changes in resistance of coil. Let us take another example of method of opposing input. We have talked about Bourdon tube. Let us consider a schematic diagram of Bourdon tube. We know that deflection of the tip is a measure of the pressure being applied inside the Bourdon tube. Now, the tip deflection depends on various factors, but for a given Bourdon tube, other things being unchanged, this tip deflection can be considered as a function of pressure alone. Among the various factors on which the tip deflection will depend, the elasticity of the material is one. So, modulus of elasticity can change with temperature. Now, if it changes sufficiently, the tip deflection can no longer be considered as a function of pressure alone. So, we can get additional deflection for changes in temperature. One solution can be, we put a bimetal strip here. Suppose we are talking about a situation where the tip of the Bourdon tube is deflecting more than it should correspond to the given pressure being applied, and that additional deflection is the result of change in ambient temperature. Now, if I can design a bimetal strip which deflects when subjected to a temperature. Okay, let me explain what a bimetal strip is. You take two different metallic strips, they have different thermal expansion coefficient. They are bonded rigidly at some temperature called T0 bonding temperature. Now, if I subject this bimetal strip to a different temperature, say a new temperature, the bimetal strip, since they have different thermal expansion coefficient, can deflect like this or can deflect like this. So, now come back to the Bourdon tube example. If I can suitably design a bimetal strip such that the extra deflection that is caused in the Bourdon tube by the change in ambient temperature and the deflection of the bimetal strip due to change in ambient temperature is same in magnitude, but opposite in direction, then this deflection of the pointer against this scale will be solely a function of this pressure. So, by putting a suitably designed bimetal strip, I can cancel out the extra deflection that has caused due to change in ambient temperature. So, this is again an example of method of opposite inputs. Now, let us talk about performance characteristics of instruments. The question you ask here is, how do you describe the quality of measurement, or how do I evaluate the performance of an instrument? There are various instruments available. If I want to compare an instrument with other possible alternatives, I must have some quantitative basis for comparison. So, performance characteristics of instruments are those quantitative bases for comparing the performance of instrument with possible alternatives. So, performance characteristics are quantitative basis for comparing the performance of an instrument with possible alternatives. Two classes of characteristics are used to evaluate or compare instruments, namely static characteristics and dynamic characteristics. Static characteristics are associated with static measurement. These are set of criteria that are used when you measure a quantity or a condition that is either constant or changes very slowly with time. So, static characteristics are those characteristics which we must consider when we want to analyze the performance of an instrument that is measuring a medium which is constant or varying very slowly with time. So, you are essentially talking about static medium or steady state situations. On the other hand, dynamic characteristics are associated with dynamic measurements. So, this is a set of criteria that are used when you measure a quantity that is rapidly varying with time. So, dynamic characteristics are those characteristics which we must consider if inputs are varying with time, while static characteristics are those characteristics which we must consider when you measure a quantity that is not varying with time. We would like to emphasize here that static characteristics also influence the quality of measurement under dynamic environment. So, static characteristics not only influence the quality of measurements under static environment, it can also influence the quality of measurement under dynamic environment, but usually we treat them separately. The reason is as follows. We will see later that the dynamic characteristics can be described usually in terms of differential equations. Now, if I want to incorporate the static characteristics onto these dynamic characteristics, the resulting differential equations will become extremely difficult to handle. So, a general procedure is to state static characteristics and dynamic characteristics separately, and we can always have a qualitative superimposition of both the characteristics to make a final choice about the instrument or to have a final say on the performance of the instruments or quality of measurements. These are the set of static characteristics we should be familiar with. As we define, these are the characteristics which we must consider when the measuring medium is not changing with time or changing very slowly with time. The static characteristics can be classified into two categories: desirable static characteristics and undesirable static characteristics. Under desirable static characteristics, we have accuracy, sensitivity and precision as various characteristics. Similarly, under undesirable static characteristics, we have static error, dead zone and drift. Dead zone can be a result of threshold or hysteresis. It can also be noted here that accuracy and static error are related in the sense that if your instrument is accurate enough, or if the desirable static characteristic accuracy is high, the undesirable static characteristic static error will be low. So, corresponding to accuracy, which is desirable static characteristic, we have static error, which is undesirable static characteristics. So, corresponding to sensitive, which is desirable, we have dead zone, which is undesirable. Corresponding to precision, which is desirable, we have drift, which is undesirable. So, let us start our discussion on static characteristics of instruments with a term called static calibration. This is a procedure used to assess the relation between the output and the input of an instrument if all influencing parameters are controlled within working range. So, calibration is the act or result of quantitative comparison between a known standard and the output of the measuring system measuring the same quantity. Calibration is accomplished by applying known magnitudes of the input and observing the measurement system output. So, what we do is as follows: all inputs, desired, interfering or modifying inputs except one are kept at some constant values. Then the one input under study is varied over some range of constant values, which causes the outputs to vary over some range of constant values. The input-output relations developed in this way comprise a static calibration valid under the stated conditions of all the other inputs. So, all inputs except one are kept at some constant values. Then one input under study is varied over some range of constant values, which causes the outputs to vary over some range of constant values. The input-output relations developed in this way comprise the static calibration, which is valid under the stated constant conditions of all the other inputs. So, essentially it is determining a relationship between input and output. So, we keep all the influencing parameters or all inputs except one constant and vary this constant over some range. Each time we note the instrument's output and can generate the relationships that exist between this set of inputs and outputs. Depending on whether the instrument is linear or non-linear, I can have a linear relationship that exists between input and output represented by a straight line, or a nonlinear curve that represents the relationship that exists between input and output. Once an instrument is selected, it must be calibrated against known standard. Let us now define the static characteristics of instruments. Range. The range of an instrument is the lowest and highest values it can measure within its specification. Span. The span of an instrument is the high end of the range minus the low end of the range. So, if I have an instrument where the lowest point of calibration is A units and the highest point of calibration is B units, then the instrument's range is A to B, the lowest point of calibration to the highest point of calibration, and the instrument span is B minus A. So, highest point of calibration minus lowest point of calibration. Resolution is the smallest amount of input signal change that the instrument can detect reliably. It should be noted that we should select instruments such that its range includes all values a process will normally encounter, including expected disturbances and possible failures. Accuracy of a measurement describes how close the measurement approaches the true value of the process variable. So, it is a measure of how close the measured value is to the true value. Accuracy can be expressed in many ways. Accurate within plus minus x% means accurate to within plus minus x% of instrument span at all points of the scale. Accuracy can also be expressed in terms of percentage true value, which can be expressed as measured value minus true value divided by true value multiplied by 100. Similarly, accuracy can also be expressed in terms of percentage full scale deflection, and this can be represented as measured value minus true value divided by maximum scale value multiplied by 100. If accuracy is a measure of how close the measured value is to the true value, static error must be the difference between the measured value and the true value of the quantity. And of course, we are talking about static characteristics, so under static condition. So, static error is the difference between the measured value and the true value of the quantity. So, true value plus static error is actually what instrument gives us as its reading. So, true value is instrument reading plus some correction factor which we call static correction. Precision is the ability of an instrument to reproduce a certain set of readings with a given accuracy. So, precision is the ability of an instrument to reproduce a certain set of readings with a given accuracy. This instrument can have high precision, low accuracy. It can have poor precision, poor accuracy, and so on and so forth. In our next class, we will see more of static characteristics and also talk about dynamic characteristics.